right, so gonna try to keep you entertained for the afternoon about distribution regression and inequality and poverty decomposition methods in reverse order. Before I say anything substantive, link to the material. So everything that I'm showing is available in a shared folder on that link, which hopefully should be active. If it doesn't, again, let me know and I will do something else. Let me copy the link on the chat, visible to everyone. We go. So material available there. That should be the files, the slides that I'm showing here. You will also find 3 PDF files, which are simple output from LISSY, and then the 3 do files, Stata do files, which actually correspond to the analysis that's being run. So we'll get to that later, but all available material is there. Up more practicalities. So I've set up a Slido page for the meeting. So on that Slido page, accessible here. So use any of your browser or mobile device, connect to that web page, enter this event code or directly go here, and you will find a Q&A box, which I think is a little easier to manage than the Q&A in Zoom. So if you have questions, feel free to post your questions there. Feel free to answer other people's questions, so I don't have to do it. And you will also see on that Slido page, there's an open poll. So if there are specific things that you would like me to talk about in this lecture, mention it in the poll. I will try to handle those. It's gonna be a bit complicated to actually accommodate all requests, but mention that. Perhaps I'll cover it. If I don't, but I see how to plug something about it, I will do. If not, that will be of interest for next year's workshop where I will try to cover this material. Again, if for whatever reason the access to the poll or access to Slido doesn't seem to work, please interrupt me and let me know. All right. Okay, so I'm Philippe Van Kerm, so I'm an economist. I'm here professor of social inequality and social policy at the University of Luxembourg and LISER. So I am currently talking to you from, I believe, that window. So here's my contact detail. You can contact me at my LISER address or at my university address. If you have any question, anything that you want to clarify about this lecture, feel free to contact me. Don't expect an answer within an hour, but I will try to get back to you if I can say something useful, and you can find some material. It's embarrassingly not updated here, but will be updated someday. Okay, what's on the menu today? Well, essentially what I want to do, it's nothing absolutely crazy. Well, the idea is just to review the practitioner's toolbox for income distribution analysis. And not all the tools, but I want to focus on tools that people are using to kind of explain, quote unquote, explain change over time or differences across populations in income or earnings or wealth distributions. And what I want to do is first cover some like well-known tools. That's going to be should be a review for most of you, and cover some slightly less well-known tools, which I'll refer to distribution regression in the broad sense. I would also, given the context of this lecture, show you implementation of all these techniques in LIS, obviously, and I'll be using Stata, so it's LIS and Stata, which I think is kind of convenient for all sorts of income distribution analysis. To be clear, I'm not going to run live code on LISSY. I think that's just not so convenient for a virtual format. But what we're going to do is I've run the analysis previously, and we're going to look at the log. So look at the code, look at the sort of output that we get, and briefly look at interpretations of the output. And clearly that's a learn how to fish sort of approach. So I want to cover methods and tools and try to clarify what they're meant to capture, where and when to use them, rather than provide any sort of substantive analysis. There will be a running example in my LIS illustrations, which are going to be closely related to a paper we had, an article we had in the most recent LIS newsletter with Petra Zauer on educational expansion and inequality. So that's going to be related to that, not replication exactly, but related material. So I suggest you have a look at the newsletter and the code at the same time to get, if you're interested into that. So what sort of research is being addressed by the sort of methods that I want to talk about in the afternoon? This whole literature that's trying to look at trends in income distribution. So change over time in an income distribution. And typical question would be, sort of what drives increases in inequality in country X or Y. So that's typically is the sort of the drivers of the change. And there's a whole literature that's been trying to do that using all sorts of different methods. Just a sample of studies mentioned here. All the references are in the slide at the end. So if you've downloaded the slide, you could look at the references here. That's obviously one very large literature. There is another big literature that is actually using the sort of methods that I want to talk about, is the one that's trying to compare distributions of income or distributions of wealth or earnings across population subgroups. And by far the most common analysis is examining differences in earnings by gender or ethnicity. These would be the big topics in that literature. So here the idea is, we have two groups and we observe distributions of earnings for one and the other, and we want to qualify the difference. But we realize that there are plenty of factors that might explain differences in earnings, education and sort of measures of human capital, the sort of jobs that people have, etc. So you want to compare the earnings, the distribution of earnings between men and women, for example, blacks and whites, controlling or adjusting for differences in characteristics. So that's a slightly different approach. They're still comparing income distributions across two groups with covariates, but here the covariates are not the primary variables of interest. It's just stuff that we want to control for in making the comparison. And then the third sort of strand in the kind of literature that I want to mention is sort of this literature that tries to look at differences across countries in income distributions, and why is there more inequality or more poverty in country A rather than country B. So that's a symmetric of that sort of question. So rather than looking over time, you look at between countries. And the reason I mentioned that is obviously because that's the sort of things that LIS is made for. So for example, what I'm showing here is sort of a scatter plot of Gini coefficients, all taken from the LIS key figures. Well, there might be more recent estimates here by now. And you see, we've got the line that connects Gini coefficients of disposable income in the US here. We've got the trend in Norway, and each line is a different country. So of course, there are questions what are the drivers of the movement along the lines? But equally, you might be interested in understanding differences between countries in inequality and in incomes. And as you can see, in general, the differences between countries are much larger than the trends over time within countries, even when those trends are kind of large and important. So that's the sort of questions that the methods that I want to talk about try to address. What are the big drivers? What I can explain, again, quote unquote, the differences in income distributions. What are the sort of variables that we're looking at in this literature? Well, typically, once you start looking at income distribution differences, well, like kind of smoking guns are, demography, population composition, age structure, migration, household formation, questions of assortative mating, fertility, household sizes, etc., etc. So there are demographic factors. You will be working with employment data, share of people unemployed, human capital, so levels of education, and the tertiary attainment is going to be my running example. Stuff about labor market structure, female labor force participation, and industrial change, all sorts of things like this. You will be looking at the returns to education, so labor market returns, self-employment, but also at non-labor incomes, and of course taxes and benefit policies that are going to reflect the state intervention. So that's the sort of variables which are broadly speaking, on the right-hand side of the equations that you may want to look at. So, well, that's, I say, drivers of distribution differences and kind of smoking guns. What I'm not going to talk about are sort of the deeper drivers, the deeper explanations and stuff like, social norms and long-term evolution of institutions, economic structures, I don't know, path dependence, geography, preference for redistribution, et cetera, which one can think of, the deeper layer of the explanations of why is distribution of income more unequal in country A than in country B, for example. So stuff like that, very important, but not the stuff that we are going to talk about today. So there'll be two parts to this session. I'm going to be talking about what I call the classics. So the classic approach to doing this sort of analysis, the classic methods. And we're going to talk and illustrate what I call the moderns, and the moderns being, using more generalized work binder sort of approaches. So the classics are, well, effectively exploiting decomposition properties of inequality and poverty measures. And I'm sure you all know that, so I'm not going to spend too much time on it. But essentially, there are two main types of approaches here. One is analysis by subgroup, where the idea is that we realize that in a distribution, let's say in Luxembourg in 2021, where there are important subsets of the populations, natives, immigrants, high educated, low educated, whatever, doesn't have to be binary. And what we want to appreciate is how much differences in income between those groups shape the overall income distribution, how much inequality within those groups shapes overall inequality, and how much the relative size of the different groups shapes income inequality. And so the idea here is that there are setups where we'll have an inequality measure, which we can actually write as a function of inequality between groups of people, inequalities within different groups of people, so there'll be k different groups of people, the population share of each group, and the average income within each group. So that's the classics and the analysis by subgroup. Now, by income source, so it's a different perspective to those questions. So the idea of the income source decomposition is to start from saying, yes, well, total income, it's the sum of components, it's earnings, it's capital income, it's transfers, it's transfers, public transfers, private transfers, et cetera, Or if you're interested in wealth, wealth is financial wealth, it's non-financial wealth, etc. It's debt and all these different. So the idea is that you'd want to understand total inequality as a function of the distribution or the inequality of each separate source, the relative share of each of the sources in total income, and the correlation between each of the source and total income. So you could imagine that if two sources are negatively correlated, they will tend to reduce inequality. If you add up two things which are negatively correlated, that's going to reduce inequality. If they are strongly correlated, if you think of assortative mating and think that's sort of an association between the earnings of men and women in a couple, for example, that might be something that increases inequality because the rich mate with the rich and the poor would mate with the poor. So that's the second type of classic inequality sort of decomposition approach. It's really nice, very simple, but that only works for specific inequality measures. So that's going to be the drawback. The other drawback is that it works well when you don't have, just have a few groups or a few sources. As soon as you want to start adding many more explanatory factors like you would do in regression analysis, that's going to be much harder. And if you want to use those approaches let's say in the cross section, and if you want to start using those decompositions to understand the change, you'll end up having lots of different parameters to look at, the evolution of the share, the evolution of within group inequality, between group inequality, and that might end up being a bit hard to interpret, but we're going to see how to do that or look at those papers. Now, the moderns sort of try to address, to a certain extent, some of the limitations of the classics. And what the moderns, would be often referred to as sort of generalized Waka-Blinder decomposition of distribution differences, which I think is an awful name, but one that I'm going to use anyway. Essentially, the idea is that instead of starting off with an inequality measure, the Gini coefficient or the mean log deviation or the tile index, and try to decompose that specific index, well, we start off with the overall distribution. And we're going to work from the overall distribution and build some statistical model for the distribution, more or less restrictive, and then create, using sort of regression framework, create counterfactual distributions that reflect the strength or the effect of factors that we might be interested in, mostly using construction of sort of what if counterfactuals. We change one factor, how would the distribution look like if we change one factor, or if you hold other factors unchanged. So generating those counterfactual distributions, and then afterwards looking at the implication in terms of Ginis, if you're interested in inequality, tile, mean log deviations, poverty rates, etc. So we are going to work with decompositions or analysis of the distribution in different ways. And then in the later stage, look at the implications of that on inequality on specific index measures, rather than start from the index measures and look at the decompositions. This comes with benefits, so not tied to those specific index measures, but it's heavier to put in place and interpretation will not always be made easier, but that's obviously a richer approach. Okay, I look at the list of participants. I'm sure you know all of that, but I still want to run through very, very quickly a quick reminder just to make sure that you are aware of all the concepts that I'm going to use or mention in the rest of the lectures. So very, very quickly, stop me if that's not clear. We're going to look at kernel density estimates. So that would be it. And what does that show? Well, let's say income or earnings or whatever is on this x-axis. And it's probably easiest to interpret the curve as showing, what's the share of the population at that specific value. That's a density, so this integrates to 1. So the value on the y-axis don't actually have much of an interpretation. Okay, that's the density function. And that's the estimator using a kernel density estimation. That's very common. The second tool is the cumulative distribution function. And that is nothing but the integral of the density function. So integrate this bit up to, let's say, 1000. And you've got the value of the CDF at 1000. So alternatively, you interpret that as showing you the probability that anyone in a distribution has an income less than whatever is on the x-axis. So in this particular example, there are about 65% of the population who have an income less than 2000. Obvious. Okay, the quantile function, also going to use the quantile function quite a bit. That's just the CDF in reverse. And I personally find that's probably the most convenient tool to actually visualize the income distribution. So you look at ranks or positions in the income distribution from poorest to richest, and the height of the curve is telling you what's the income at that particular level. And so obviously, if you look at 0.5, you've got the median here. The median would be 1800 approximately. Okay, that's also called the Pence parade, but that's just the quantile function. All right, Lorentz curve that you all know. So I'm not going to tell more about the Lorentz curve. So cumulative population share, cumulative income share. The more bended the Lorentz curve is, the more unequal the distribution of income is. And so the Gini coefficient as an index of inequality is picking up the area between the diagonal and the Lorentz curve. So the more both the Lorentz curve, the higher the Gini coefficient. Gini coefficient, which has all sorts of different definitions, which I don't want to talk about here. All right, Gini coefficient, we're going to look at Gini coefficients, but we're also going to use other sorts of measures. Okay, the variance, I'm not going to insult you in telling you what the variance is. Coefficient of variation, that's just the variance divided by, the standard deviation, sorry, divided by the mean, which makes the measure relative. Also been using interquintile ratios or percentile ratios, income share ratios, top income shares. All of these things are very popular. Not really useful in terms of decompositions. There's hardly any simple decompositions of those measures. But once we apply, of course, the modern approach, this sort of generalized Waka blinder, we will be modeling the distribution, and we'll be able to summarize the change and the factors in terms of top income shares, if that's what we're interested in. And finally, the last important component that we all need to know to follow this lecture is the generalized entropy family of inequality measures, which is a different sort of, Lorentz consistent inequality index. Lorentz is consistent, meaning, if a Lorentz curve is below another one, there's going to be higher inequality according to those generalized entropy measures too. So we've got the tile index, the mean log deviation, and the general expression for the generalized entropy measure, which is this one. And I'm not going to look into the details. I'm sure you're familiar with that. Just one note is that this generalized entropy 2 is equal to half the square of the coefficient of variation. And as you will see, that's going to be relevant to the methods that we show. So that perhaps something that's important to bear in mind. If we pick up a low value for alpha, and a low value for alpha can be negative. So let's say GE minus 1 or GE 0, so the mean log deviation. That's an index that's going to be more sensitive to income differences at the bottom. If we pick up a higher value of alpha, such that 2, like GE2, that's going to be pretty sensitive to higher values in the distribution. And I should say that I think it's just too sensitive to the values at the top of the distribution. So if, for example, which implies that the estimates that you're going to get are going to be very heavily influenced by the higher values in your sample. And for example, if you're working with loose and net worth distributions, The net worth has a very long tail, so there are very, very, very large values in the sample. Well, the implication is that essentially your inequality, your GE2 inequality measure is simply going to reflect the values of the largest observations in your sample. So that's not great, but it's got very interesting theoretical properties. Practically, I think one should be very wary about using those. And finally, last bit, poverty. That's again something you all know. The idea of poverty is that you set up a poverty line and you look at the shortfall, income shortfall to the poverty line. And poverty rate is just the proportion of population for which the income shortfall is positive. So we have an income below the poverty line. And the FGT measures is just the average of the shortfall raised to the alpha power. So if it's 1, it's just the average shortfall. If it's 2, it's the average of the square of the shortfall, etc., etc. And it's rarely used with an alpha above 2. Okay, that's the toolkit. And let's look at the classics first. So decomposition approaches. First, by income source. So think of, I can skip that very quickly. We're interested in your household income. It's some of different components, market income, public transfers, pensions, and it's minus taxes and social security contribution, etc., etc. So what you want to do is, in this context, you want to understand, what's the contribution of, say, capital income to, or the contribution of the change in capital incomes to the change in income inequality, or the increase in inequality, or how much do transfers reduce inequality. You may be interested in decomposition by income sources. And the most frequently used decomposition is very, very simple. It's the rule that's developed in those 2 papers by Tony Sharrox. And essentially, it simply says that the share, so the contribution of a particular source J here, to inequality is the product of 3 terms. One is the inequality within that particular source, measured by the coefficient of variation, divided by the overall coefficient of variation of total income, times the relative importance of that source, so the average of that source divided by the grand mean, so that's effectively measuring the relative importance of the source in the total, multiplied by the correlation between this particular source and total incomes. Multiply the 3, and you've got the contribution of source J to total inequality. That's very simple, and under some axioms, this can be interpreted as being valid for any inequality measure. That's a natural decomposition for the coefficient of variation, and therefore the GE2. It can also be considered valid for any relative inequality measure, if you buy some more axioms, which I don't want to enter into. That's the Sharrox rule. The other big composition by source is the decomposition of the Gini coefficient, which is, so that's referred to as the Lerman-Nitzaki decomposition, and it's effectively the same up to a slight difference. So the idea is that Gini coefficient is also the sum of contributions of different sources, K sources, which is here also the product of 3 things, virtually the same: the relative size of the source, the concentration of the source with respect to total, and the concentration is measured by the Gini coefficient of that particular source and the correlation between that source and total income. So as you see, pretty much the same as the Sharrox decomposition. The only difference is that the correlation is here measured with the so-called Gini correlation, which is an income to rank correlation rather than a Pearson correlation. But that's pretty much interpreted the same way. So once you've done that, if you're interested in the change, so here is sort of calculating the contribution of a source to a particular cross-section. But if you're interested in the change, so understanding the contribution of a source to the evolution of inequality, well, you can trivially do these sort of additions and subtractions. So you can write the change here in the Gini coefficient as the change in the relative size of the source. So if capital income been growing a lot in the distribution, so its share has been growing. So that might contribute to the change in the Gini coefficient, holding the concentration coefficients constant, plus the change in the concentration coefficient, holding the share of the source constant, and furthermore, splitting the change in the concentration coefficient as the change in the Gini coefficient of the source and the change in the correlation between the source and the total. And every time we have to hold the other 2 components. It's a multiplication of 3. So obviously, once you change 1, you look at the effect of changing 1, you've got to hold the other 2 constant at some value. Okay, so that's trivial, easy. That helps getting a sense of the relative contribution of those three factors: the change in the source, the change in the share, and the change in the correlation, the association between the share, the source, and the total. But the problem here is that you face a problem that we are going to face again and again and again in pretty much all our decomposition. You face an index number issue, which is, well, two things. And let's say you decide to apply that specific formula, but you could say, well, why not flipping the signs, setting the zeros to ones and the ones to zeros? And you'd end up with actually a different decomposition from the original one. That's simply because this decomposition is, you need to decompose multiplicative terms. So whether you go one direction or the other direction, you're not going to have the same contribution of each source, not minus the contribution of each of the sources. So that's one thing. And the other variant of that same problem is that effectively, once you look at the change in, let's say, the share of a particular source, well, you're looking at the effect of the share by holding the within group Gini coefficients to the first period or to the second period. Both are equally valid, but they're going to lead to potentially different estimates of the contribution of the source. One solution to that is the thing called the Shapley value. And if there is interest in a quick explanation of what the Shapley value is, I'm going to talk about that in the lecture. Actually, let me have a look. Let me assess if there is any sort of interest in having a quick look at the Shapley value. I don't exactly know how many participants there are. So I will say that if there's more than 8 yes, I would go for it. So I count 1, 2, 3, 4, 5. Okay, I will do a bit on the Shapley value. So what I've just described, so this Shorrock's rule or the Lerman-Itzhaki decomposition of the Gini coefficient is based on a mathematical decomposition of the index, whether it's the coefficient of variation, whether it's the Gini coefficient. They just write up the expression for the Gini in terms of those three terms: the share, the Gini of the source, and the correlation with the total. Now, there's another way to actually try to do these sort of exercises. Is more in terms of sort of simulation-based. And the idea of a more simulation-based approach is, so we start with the distribution with our data on total incomes, and we do simulations of the data. And one way to do it in the context of income source, measuring the contribution of income sources, the idea is, well, let's shut off inequality in one of the sources. And how could we shut off inequality in one of the sources is, well, let's imagine that one source did not exist. So let's set all incomes to 0 for a particular source. So let's think of household incomes. We've got earnings, we've got capital incomes, and we've got, let's say, transfers. And we want to know, well, how much does capital income contribute to inequality? One way to sort of get a sense of that is say, well, let's imagine that there were no capital income. So we just add up earnings and transfers and look at inequality. And we then compare, is there more or less inequality if we discard or if we disregard capital incomes? That's the idea. That's completely independent on any inequality measure. It's more a simulation sort of approach. So we've got our data, sort of do some manipulations to the data, and let's see what we get. So if capital income were a big source, very unequal, whatever, big contributions to household incomes, you'd imagine that shutting off inequality or disregarding capital income entirely would have a big impact. It's entirely negligible, just it's a small thing in the total. Well, you can switch it off. That's not going to have a big impact on the total inequality. So you do the simulation, and then you summarize with capital income, without capital income, with any sort of inequality measure that you like. So the Gini, the generalized entropy, the variance, you may be interested in looking at its impact on poverty measures, whatever, polarization, richness, top income shares, any inequality index that you like. You're not stuck with the Gini or a generalized entropy measure. So that's the idea of a more simulation-based approach to assess the contribution of different income sources to total inequality or total distribution. So that's, of course, one strategy. But once you start thinking in terms of simulations of that sort, you could do, I can do better than just disregarded capital income. What we could do is, let's assume that everyone receives the same amount of capital income. So you take the average capital income in your data, and you assign the average capital income to everyone. So that's another way to sort of shut off inequality in capital income, but not disregard the source entirely. You still take into account the fact that capital income contributes to the total. And so you add up, you remove capital income, and you add up the average. And again, you compare inequality using whatever index you like in the total to inequality that you observe if you shut off inequality in one particular source. Easy, clean, and flexible in the sense that you could apply it to any sort of inequality measure you like. But there's one little catch, is that that is not a decomposition. Imagine you do that for, say, you have 3 sources, and you do this little exercise for each of the 3 sources. Well, the contributions of each source are not going to add up to the total inequality. So it's not a decomposition in that sense. A decomposition would mean you could add up the components, you've got the total. If we do that here, it doesn't add up to the total. So one way to make it add up to the total is to say, well, let's start with 3 sources. We've got labor income, capital income, transfers. So let's first look at the impact of, let's say, capital income. This was my example. So I'm going to compare inequality in the total to inequality if I disregard inequality in capital income. Okay, this is one component. That's the contribution of capital. But now, instead of removing labor income from the total, I'm going to keep going from that simulation. So what we're going to do is sort of look at the distribution when there's only labor income and transfers. Let's shut off labor income. And so we compare inequality when there's only labor income and transfers to inequality when there's only transfers. And that would be the contribution. Okay, let's go and see contribution of labor. And then, of course, we could keep going. We have an estimate that the contribution of transfer would be inequality of transfer minus inequality when there's nothing. So we'd assume to be 0. No inequality when everyone's got nothing. If you do that, then you could do the trivial arithmetic for yourself. Adding up the 3 terms returns inequality in the total. That's obvious. Now we've got a decomposition. So by having a sequence of elimination of inequality in the different sources, starting from capital, then labor, then transfer, we have 3 contributions, and the 3 contributions add up to total inequality. Problem is variation of the index number problem that I mentioned above. While this appears totally arbitrary to have done capital, then labor, then transfer. So you could do labor, then capital, then transfer, or you could do transfer, then capital, then labor, then whatever. All combinations appear in this particular context equally valid, and each of the different sequence would give you a different contribution of the sources, which is not very appealing thing. Whatever sequence you choose, you'd have a different contribution. And that's where the so-called Shapley value has been advocated, is to sort of address that arbitrariness or the dependence on the sequence. And that's what we have here. So this is exactly the example that I've been showing. We have 3 sources, J sources in this example, J being 3, and think of coalitions of sources. So the Shapley value has been developed in the literature where thinking in terms of coalitions of people. But here, imagine coalitions of sources. So think of coalitions of sources, and a coalition can be adding up everything, or you make coalitions of just 2, or you make coalitions of only 1, or you make a coalition of nothing, and then you've got 0. So these are 2 to the power J potential combinations of sources. Given those 2 to the power J different combinations, there are, with 3 sources, 4 potential ways to measure the contribution of each source. So here, labor. I was using capital previously. Here, focus on labor. So the contribution of labor can be measured in a coalition with capital and transfer versus a coalition where labor is dropped from those 3. The effect of labor when only capital income is added, the effect of labor when it's matched with transfers, and the effect of labor when it's alone. So there are 4 potential different values for the contribution of labor income. So what is the Shapley value? It's a form of average of all these 4 potential values. And the idea is that you add up, so you take the average, take the average of the contribution in each of the 4 coalitions, but that's simply what this is actually doing. Each of the 4 contributions is weighted so that each coalition size receives an equal weight. You see here we've got one possibility. So 1, 2, 3, 4, 5, 6, 7, 8. So coalitions of 3, there's 1 chance in 8. So this is going to be 3/8. Each of coalitions of 2, when the effect is measured like this one or this one, is going to have a weight of 1/8. Coalitions of 1 are also going to have a weight of 1/8, and coalitions of 0 are going to be weighted 3/8 because there's only one possibility. There's a good chance that I'm getting the arithmetics wrong because I don't recall if I should add up those contributions or those contributions. You'll check the factorials, but that's the idea. So it's not just an average of all the potential contributions given different sequences. It's an average where each of the contribution is weighted such that each size of coalition is weighted equally. And the good news is now that we still have a decomposition. So if you do that, add up the contribution, this adds up to the total inequality. So the sum of CJ is inequality in the three sources, but it also does not depend on the order of the sequence because effectively you do all potential simulations and you take some form of average of that. That's effectively what a Shapley decomposition is. So it's sort of whenever there's dependence on the sequence, so whenever the results depend on the sequence in which you do your simulations, you can do all potential sequences, thinking in terms of coalition. So what are the factors which are eliminated? This is in the context of income source decomposition. This applies to other sort of simulations. So in all of those simulations, you're going to sort of handle one factor at a time. So you think in terms of combinations of factors which are controlled for, which are not yet controlled for, do all of them, do a form of estimate the contribution in each of the simulations, and take a weighted average of that. So that's kind of nice in terms of doesn't depend on the sequence anymore. Of course, the problem is that trivial simulation like this, that's easy. But if you have a simulation that has, requires lots of, estimation time and then, complicated stuff, this can be computationally expensive because you'll have to do all sorts of all these potential sequences. So that can be heavy. And no, there's also this issue that, if interpreting contributions in terms of averages might potentially turn out to be a bit complicated. It's kind of reasonably clear to interpret, what's the contribution of capital once you shut off capital from all the other sources. But the average of the contribution of capital when you've got different combinations of remaining sources, I potentially think that it's hard to interpret. So that there's pros and cons, but there's a very good chance that if ever you write a paper that depends on the choice of a particular sequence of factors or sources, you'll have a reviewer that's going to say, well, but how sensitive is that to a different sequence? Please do a Shapley value decomposition. If that's what you get as a comment, well, your answer will be to do that sort of thing and check the sensitivity of your results. And again, that's not completely complicated conceptually, but that requires a bit of coding, and you'll have to make sure that your code, when you do it on the LISSY, is sort of clean and easy to actually to do with all these sequencing. So there's a bit of programming involved, but that's conceptually not all that complicated, I think. So the second classic decomposition, so these examples with different sources, contribution of different sources to the total, one big family. The other big family is probably even actually easier to implement. Most obvious one that you'd think of is decompositions by population characteristics. Decomposition by population characteristics simply recognizes that, you've got a population of, I don't know, the talls, the median, the shorts, and the tiny people. They form the overall population. So you partition your population into mutually exclusive subgroups. And let's say those in between are the unidentified. And you want to know what's the contribution of each of those groups to total inequality. So partition urban, rural, or the forms of inequality, the north versus the south. Age groups, that's a very common sort of partition. You could partition by gender, education, industries, and there's all sort of partitions that you could think of. But you have to think of a partition that is discrete. Okay? You sort of have a fixed number of classes, types, and you define those types in such a way that you still have enough observations in your data such that you can still estimate something within that group. Got this partition, start off with the partition. And then the contributions, what you're trying to measure is how much inequality between the incomes of people of the same type. So how much of within group inequality contributes to the total versus how much between group inequality contributes to the total. And between group inequality is defined as its inequality in the average incomes of the groups. And it's very common, for example, to think in terms of rural versus urban divide as, how much of total inequality is due to income differences between people in cities and people in the countryside versus inequalities in incomes for people within each of those groups. And then the third part of that is, of course, if you think in terms of the change, is in terms of the relative size of those groups. And what we do, for example, what we discuss in the LIS newsletter is simply saying, well, if you think in terms of education, so we're thinking in terms of tertiary education, there's many more people having tertiary education, but we appreciate that, there is inequality in incomes or in wages for people with the same education, but there's also a lot of inequality or income differences in the earnings of people with different sorts of education level. We combine that with gender also. So what we're trying to look at is whether and how much the change, the expansion of tertiary education, how much of the fact that there's more and more people with tertiary education, how much does that contribute to the evolution over time in inequality in different countries? And so obviously the answers depend on how many more people are tertiary educated. What is the return to education? So what's the difference in average incomes for people without tertiary education compared to people with tertiary education? So that's the between component, if you like. The return to education would be the between component. And what's the contribution of inequality among people with the same level of education? Not everyone's got the same earnings. So if you think of residual inequality, so that's the third part. And what we're trying to do is, what's the contribution of those three components? That's a very simple question. So technically, how does that work? Well, it doesn't work all that well, actually. Problem is that most inequality measures cannot be written in any simple way like I've just described. So you can't add up between and within group inequality and get to total inequality. That doesn't work. Except for one specific type of inequality measures, the generalized entropy family, which is the reason why I mentioned them. So if you look at the generalized entropy, you can actually write it as the sum of two bits. This bit. One is the between group, so inequality in the average incomes in the different subsets that you've defined. And the second component is inequality within the groups, where inequality within the groups that's inequality within each of the K groups that you have defined, where the inequality within each of the group is weighted by this term. And that's a bit of a strange expression. So depending on alpha, so recall alpha 0 is the mean log deviation, alpha equal to 1 is the tile index, alpha equal to 2 would be the generalized entropy 2, and you can go to -1. So you're picking up the alpha, means putting more emphasis on income differences at the bottom for low alpha, at the top for high alpha. Once you've set it up, this defines the contribution of each of the groups. So if you look at the mean log deviation, this term is the relative share, the share of the group in total income. And that is the share of group K in total population. So one is weighted by income, so the contribution to total incomes. The other one is contribution to population share. So the incomes of the population don't count if alpha is equal to 1, for example. 1 minus 1, 0. So that term disappears. So if you do the tile index, so alpha equal to 1, 1 minus 1 is 0. So this term disappears. So for the tile, you take the average of inequality within each of the groups, weighted by the contribution of each group to total income. Okay, so if one group is very, very rich and the other groups are very, very poor, the very, very rich is inequality in the very, very rich is going to count a lot in the total within group. If, on the contrary, you work with the mean log deviation, so alpha is 0. So if alpha is 0, this term disappears. These terms become 1. So if the mean log deviation, what you do is you look at the mean log deviation in each of the type of the groups, and you take the average, where the average is weighted by the share of the population size. That's a bit of a strange properties of this decomposition, but that's what it is. And now, of course, if you use alpha is equal to 2 or something else, you'll see it's a combination of both the relative contribution to the population and relative contribution to the total incomes that's going to weight each of the within group. So it's nicely additive. Now you can write it total as the sum of a between and the within. But once you define the within, depending on the index measure that you use, it's going to be inequality within the group weighted by size in incomes or the size in the population, which is a bit of but otherwise simple. If you compare that to the Gini coefficient, for example, well, the Gini coefficient, as is, I think, well known, it's not decomposable by subgroup. So you cannot write the Gini as total Gini being the Gini of between group inequality. So between group inequality would be defined as inequality of the Gini when everyone in the group is receiving the average income in the group, plus some sort of a within group Gini. So Gini, some sort of a measure of an average of the Gini within each of the groups, okay, like this. Yeah, sorry. If you discard this bit, that is wrong. So it is not true that the Gini is the sum of those two simple terms. There is a third term, which is often written R for either residual term, which would suggest that there's no interpretation to that, or for a re-ranking term, means that the Gini is defined on the basis of ranks. And of course, there are differences in the rank of a person within his own group or her own group, and the rank of that person in the total. And in fact, it's the difference between the ranks of people in their own group and the rank that these people would have in the total that actually is being picked up by this R term. So if everyone's got the same rank in the total and the population scaled by, the population is located, this term may disappear, but in general, it's not actually zero. So Gini decompositions by subgroup usually are not very helpful because these can be of all sorts of different sizes. Okay, and then finally, if you're interested in poverty, then you're happy because poverty is obviously trivially decomposable by subgroups, because the FGT, so the Forster-Greer-and-Thorbecke, whether it's the headcount ratio or the poverty gap, whatever, depending on values of alpha, it's simply an average. So it's either the average of people who are poor, so that's an average of 0.1 is just the poverty rate, so it's probability. So of course, you can simply calculate the proportion of people poor in each of the groups and weight the groups by the group size, and you've got a decomposition of the total. So that's completely trivial, as long as you assume that the poverty line is the same in all subgroups. That's an obvious point. That's easy, very, very commonly used, and often very useful to start with. But in a lot of applications, you are sort of hitting the wall because you want to know, oh, yes, but I'm adjusting for education. But of course, it's not just education. There are age distribution is changing. People are working in different industries also. So if I look at the effect of education over time on earnings, but I want to account for the fact that industries are changing, that there's more women in the labor market. So that is also contribution to this. So I want to have multiple variables in the analysis. And well, if you want to stick to those decompositions, what you need to do is sort of either split the data in sort of interaction cells, or we've got very small cells defined by combinations of variables, but very quickly you end up with cells which are just too small. There's not enough observations in your data to actually calculate the, say, within inequality measures. So, well, you're stuck there. Then you could think of, oh, but I could do smoothing techniques. You could do some sort of defining, having fuzzy classifications where you have groups of people which are similar, and each of the similar groups contribute to the total. So you could conceivably think of a smooth subgroup decomposition. In practice, I don't think I've ever seen that done, but that's conceivably doable. Practically, not much of a way out in those decompositions once you've got many groups. I'm just going to describe, I don't like it very much, but I still want to describe it because it addresses that specific point. Alternatively, you move to the sort of approaches which I'm going to describe in the second part of this session. All right, so the example in LIS, this last one, the so-called Morduc and secular decomposition. And actually, as you will see, this is a combination of the subgroup decomposition and the source decomposition. So just mix the two and you've got something that might be useful. Let's look at that. So the idea is really very simple. The idea of Morduc and secular, and actually that's the central paper by Gary Fields is a nice application as well, and there's a sort of deeper discussion in Cowen and Fior here. The idea is very simple. Okay, let's first do a regression. So we've got total income or earnings, whatever. Let's first do a regression of that on variables, typically as you define them in any sort of regression. For example, earnings, and you have, let's say, low education and high education, leaving out median education. You may have age, industries, all the potential explanatory factors that you may want to look at. So essentially, you first do a regression of the variable of interest and the explanatory variables. So once you've done that, you look at this expression and you say, oh, but that is a factor decomposition. We can say that total income is the contribution of the addition of different sources, where each source is the product of the regression coefficient and the value of that variable. So you could just say that this is just a factor decomposition of incomes, as we said before. This would be capital, this was labor, and this is transfers. Except that no, this is an artificial source that's constructed by multiplying the regression coefficient with the explanatory variable. Easy enough. In a sense, it's very similar to thinking in terms of partial R squares. When you want to look at the contribution of a particular explanatory variable to total R square, it's a bit like the same idea. So that's all. First, the regression. You get the coefficients, you create the sources. So a little implementation trick is that once you have, let's say if you have dummy variables, when I described it, I said, well, this is low education, the second is high education. Well, you will add the two, and that's going to be one source. So that's going to be the source education. And maybe you'll have, or should have done three. Age, okay, you're going to have a source age by, if it's taken continuous. If you have age and age square, those two would be lumped together to be the contribution of age, etc., etc. Do that, run a simple decomposition by source, and you will be able to see, think again of the three contributions. So one is the share. And so the share of the source is going to depend on, how much variation there is and the value of the coefficient. If the coefficient is 0, so if that variable doesn't contribute anything to the outcome, the total is going to be close to 0. So the share is going to be close to 0. So that's going to contribute very little to total inequality. The second one is inequality in that particular source, and that's going to be driven by differences in the values of X in the population, say age. And if age varies a lot in the population, well, that's going to be weighted by the coefficient, and inequality into that is going to be a driver of inequality in the total. And then finally, you've got the correlation between the sources, and that's going to be mostly driven by the empirical association between, for example, age and education. So if age and education are very correlated, they are jointly going to contribute more to total inequality. That's pretty nice. I think I would convince myself that it's very useful when I describe it in this way, except that once you start doing it, one issue is that usually what you will end up with is that the big source is going to be the residual. Most often the distribution, because the residual is going to be one of the sources, and effectively inequality in the residual is often going to be the biggest contributor to inequality, which means in the end, you don't know. It's just residual distribution, which is not hugely appealing. You'd agree with me. And then you will also start thinking that, well, but maybe those results that I get, they depend on the specification. So how did I define dummy variables? What variables did I include? Shouldn't I use interaction terms? Is additivity, so linearity in the regression specification, is that appropriate? And you'll see that this has implications on the sort of estimates of the contribution that you find. So that's all I wanted to say. Sort of looking through those decomposition approach, the classic approaches based on decompositions. Again, I imagine this is well known, but I think it's sometimes useful to actually step back and look at how these things combine. Let's have a relatively quick look at an implementation of some of this stuff in LISSY. So before I move there, just mention there's all sorts of Stata routines which help you do these calculations. As you see, nothing's complicated, just recalculating inequality within the groups or between the groups and adding and subtracting and multiplying. So it's sort of all trivial operations, but still that can be tedious. So there's a few useful Stata routines. So there's one called Inequality by Stephen Jenkins, which does this decomposition by sources. LIS can also be implemented for the Gini using this SGini, which I've written a while ago, and another piece called Desco Gini doing pretty much the same thing, but a little bit differently and allowing weight. So I, of course, advocate for SGini, but Desco Gini is good enough, absolutely. Inequdeco for decompositions by subgroups. So that's the generalized entropy decomposition by subgroups, again by Stephen. PovDeco, that's the trivial poverty decomposition by subgroups. There is a command called ineqrbd, and I confess I forgot why RBD regression. I forgot what RBD means, but that's applying the Morduk and secular regression approach. There's another one called gfields, which is doing the same estimation. If you still want to look at Gini decompositions by subgroups, there's an analogy package which does this Gini decomposition by subgroups and estimates the overlap term, so this R term in my slides. And there's an MS deco for Mukherjee and Shorrock's contribution to groups to change. And that's effectively applying subgroup decomposition, but to 2 time periods. And so it's evaluating the contribution of change in the share, change in the within group inequality, change in the between group inequality to the change over time in an income distribution. Okay, some illustrations of that in another file. So I've got an example. So what did I do? I went into LISSY, started LIS, selected Stata as software, and I submitted a Stata script, which you will find in the drop it folder. If you haven't looked at it, you can find it there. So I first ran a data preparation script, which essentially is building up a small data set, which I'm going to use for the illustration. So what I'm showing you here is data preparation. You get a sense of what sort of data I'm going to do my illustrations with. So I did that, ran it on LISSY, and then just downloaded the output, and we look at the output here. You can run it for yourself, try it. If you take the do file, which is in the drop it folder, copy, paste it into the LISSY, run it, it should run for you. And you should get the same output as I've got here. If you want to do stuff seriously, all sorts of countries, many years, you will want to loop across all these different countries and years. For my illustrations, I won't. So I sort of have a smaller set of countries, Spain and Luxembourg, and actually all my examples will be based on Spain. So what do I do? Here it's actually the data preparation that we use for the LIS newsletter. So what we do here is we're trying to combine multiple years. So I'm going to create a data set, well, actually one data set with 2 data sets stacked on top of each other, more precisely. One is combination of years, of survey years in the 90s. The other one is a combination of survey years in the 2000s. So one is from 93 to 97. The other one is from 2003 to 2007. And I realize, I think this is not actually the example in the LIS newsletter. Doesn't matter. So 2 time periods, whatever. And so what am I doing here? If you followed the last Friday's session, you know what a local macro is. So here I'm sort of storing those values into a variable called years 90, and well, local macro, not variable. Let's talk data. And another local macro containing the values 03, 04, 05, 06, 07. And I've got this macro here, which contains S and loop, so just countries over which I'm going to loop. For each C of local country means I'm going to loop across all the different values of the local country. And each time I'm going to run in a loop, C is going to pick up one of the values in sequence. So the first one is going to pick up C equal to Spain. Second round is going to be Luxembourg. So for one of those countries, I am going to first clear memory, then loop, another loop. So all this stuff in the do file is nicely indented. This output is sort of squeezed here, unfortunately, in the LISSY log. Appending data sets. So what's the data set? This is Spain. This is for different values in the local years. So that would be Spain 93, Spain 94, 95, 96, 97. Each time picking up the P file, and I'm just appending all the files. I'm stacking them on top of each other with a capture in front of that. So if the data doesn't actually exist, so if that particular survey is just not available for a particular year, it's just not going to stop, keeps on going without any complaint. So just stacking different years. You can start with an empty data set and just directly append to emptiness. You don't actually have to use and then append. That's a little trick that's worth knowing. That bit, call it period 0. That's all the 90s data set stacked on top of each other. Repeat the same thing for the 2000s data set. So stacking up the 2003, 4, 5, 6, 7 data sets, whatever is available. And that's going to be period 1. So I replace that variable period for 0 here, replace it with 1 if it's missing, and it's missing because I'm just adding stuff which weren't there when the variable period was defined. Okay, then I think the rest is just nothing very important, just dropping some data I don't want to use or missing data, defining some additional variables. So there's one that's going to be one I'm going to use throughout, whether the person has tertiary education and whether the person is reporting having completed education. So I focus on people aged less than 65 at work who have completed their education. And the variable which the illustration is going to be using is annual labor income, which is because I just want to be bothered in this particular case with extreme values. We truncate to the first and the 99th percentile of the distribution. And while taking logs here, I'm not actually going to use that very much. And there's one key variable which is going to be important in most of the in the illustrations is this one here, the sex, which is a combination of tertiary education and gender. So that's going to be 1 for male without tertiary education, 2 for women without tertiary education, 11 for men with tertiary education, and 12 for women with tertiary education. And that's is exactly just defining dummies for those 4 different levels. That's what I'm using here. And you'll see why I need both the variable categories and the dummies here. Just keep only the variables I need. I don't want to have too much of a big data set in LISSY at the same time. So I just keep the variables that I need. And important, I'm saving the data in my own directory that I can access later on in the second session. Okay, so we have this data set for Spain and the same data set for Luxembourg. So multiple years stacked for period 1, multiple years for period 0, period 1, and this capped earnings income variable and various standard explanatory variable, notably tertiary education and its interaction with gender. So that's my data preparation. And now let's try to do some decomposition analysis of that. So launched a second job. Now let's just focus on Spain. Again, real application would have more countries and more complicated stuff. This is just Spain. I get back to my folder where I saved extract S for extract for Spain. Very important. First line, before you do any sort of estimations, my recommendation is specify SVY set. Even if you don't really use it, it's good practice to do it. It forces you to think about what are the weighting variables, what are the stratification variables, stuff like that. So sampling weights, that you've heard about that, but sort of what are those sampling weight variables? So here I'm using personal files, so it's just the p-pop weight. That's the sampling weight. Important, primary sampling unit is the smallest, the level of clusters of observations. And here I'd recommend usually to work with the HID. So this is the personal file. So you might have multiple adults in your data set that belong to the same file. Those adults are going to be correlated. I mean, there's associations of people within the household. That's obvious. So that has to be a primary sampling unit. So you have to specify. If you work with individual level data, specify the PSU as HID. There's probably more relevant variables. There's probably higher level primary sampling units in the specific surveys that have been collected to and integrated into LIS. But unfortunately, usually you just don't know. So if you knew which are the real cluster variables according to the sampling design, you could use it here. But unfortunately, usually you can't. So specify primary sampling unit as the HID, household ID. And here, there's also a stratification variable. So usually you wouldn't know that the stratification is the feature of the design. Usually you just don't know in LIS if if the data was stratified by what. But in my example here, recall I've been stacking data sets like this. This was, let's say, 95, and I don't know, 97 and 99. So I've been stacking data sets and also data from the 2000s, let's say 03 and 05. So I've been stacking multiple years. So I know that each of those data sets is an independent sample, and that's the definition of a stratification variable. So I know that at the very least, observation from different years are actually coming from different strata. So that at least should be specified as a strata. So the year needs to be specified as a strata in this example. So if you stack different data sets for different years, don't forget to specify year as the stratification variable. Okay, my example, that's the SVY set. If you do different combinations of data, same thing, if you combine different countries, these are obviously different strata. So if you combine different countries, use country as a strata. And if you combine years and countries, each combination of the two should be a strata. All right, SVY set. So just telling Stata, this is more or less the working sample design in the specification of the data that's in memory. So I'm just now looking at the evolution of tertiary education by gender in the 2 periods here, specifying the sampling weights. Here I'm looking at the average earnings by tertiary education and sex interaction. And this little bit here, the SVY prefix, because I want Stata to use the survey weights I want to instead use this specification and calculate the standard errors and the confidence interval for my estimate of the average earnings, taking those design variables into account. So SVY. And I want to have it for period 0 and period 1 separately. So that's the subpop if specification for SVY. And then let me go on until 35 and then I stop. Let's look at the code here. And then we do those simple calculations. So Inequality, that's for subgroup decompositions. Cap earn, that's my uncapped earnings variable. For period 0, for period 1, specify the sampling weights. And just by specifying by the sex, which defines the types, this means that Inequality needs to do the calculations and the subgroup decomposition. And that's going to be done for the 2 time periods separately. The Morduk secular decomposition of the same thing. Well, that's Inequality RBD cap earn. And here, because it's going to use a regression framework to actually do that, in modern Stata, you would specify I.the_sex. Okay. But many user-written commands don't allow factor notation. So that's why you'd need to actually generate by hand the dummy variables and specify it here. So that's what we do. This is the regression specification, if you like. I could have added more covariates because it's a regression specification. You're not limited to just a small number of covariates. You could put more. I just want to have a comparison of the 2 approaches here. So that's going to create factors for each of those variables and treat them as a different source and do an income source decomposition. And now, of course, once you've got that, you could start, that's for each of the periods separately, but I could now try and create counterfactual scenarios where, what would be inequality if, for example, how would inequality look like if I Inequality cap earn period 0, that's the same one as this one here. Now, suppose you know that Stata estimates stuff, and then you can collect the estimates in the so-called return results or E-class results, and this is an R-class or R results. So these are values calculated from the command, which I can pick up. So the names of the estimates here are, you need to look at the help file to know what they are. So this is the estimate of the between group contribution to the mean log deviation, so GE0, mean log deviation. That's the share of the incomes. That's the mean log deviation for group 1, mean log deviation for group 2, for group 12, and for group 11. So that's actually, you'll recognize, that's the expression of total Gini. So that's the total mean log deviation by subgroup. If I display those results, you're going to see total inequality as measured by this one here. I'm saving it here in local macros. That's what I'm doing in this little loop. And the only exercise I want to show is that now I recalculated same contributions for period 1. And now we can combine estimates from the 2 to actually create a counterfactual inequality, which is what would be inequality in period 1 if within group inequality factor is picked up from period 0. And that's what we get here. Is here take the between from the last estimation, so for period 1, the share of each group from period 1. But here I'm plugging in the within group inequality from the value which I had saved from period 0. So these are correspond to period 0. These are values for period 1. Combine the 2, and that line is going to give us how would inequality look like if I fixed inequality within the groups to the previous period, but allow the between group and the shares to change. That's a simple way to have bootstrap estimates of standard errors for those sorts of calculations. That's here and going on here. I stop now, and then that's it.